Welcome to the explainer that is going to fundamentally change how you look at your computer science exams. I'm talking about a massive, paradigm-shifting change in your approach. Because here is the absolute truth that most students never realize. There is no paper. There are only patterns. Once you learn to actually see the underlying code behind every single question, the entire exam becomes entirely predictable. It's like a giant puzzle, and we're about to give you the exact box picture. Today, we are focusing laser-tight on one of the most critical make-or-break areas in the Cambridge 9618 syllabus, object-oriented programming, or OOP, terminology. Specifically, we're talking about objects, properties, attributes, methods, and classes. Now, you might be wondering why we are so focused on terminology. It's because the difference between sitting at a B grade and securing that elite A-star grade almost always comes down to mastering exactly how to apply this terminology in unfamiliar contexts. I see two types of students all the time. Let's call them Alex and Sam. Picture the exam room, the clock is ticking down, the tension is building. When faced with a complex past paper question like Cambridge Paper Code 9713, Alex panics and overloads the page with raw computer science facts. Alex writes paragraphs of textbook definitions but provides absolutely no analytical depth. On the other hand, you have Sam. Sam just rushes. Sam looks at the clock, completely misses the command word requirements, writes a few fragmented bullet points, and moves on. We've all been there, right? You look at their answers side by side, and it's just a sea of brutal red pen marks from the examiner. Today, we're going to take those flawed answers, and we're going to transform them into A-star responses live. We're going to turn those red marks into green check marks. And whether you are currently studying syllabus 0417, 0478, 0983, 0984, 2210, or our main focus today, the 9618 advanced level, this methodical, strategic framework applies perfectly to you.
Okay, let's dive right into this and map out our examiner's playbook. We have 4 key sections today. First, core OOP principles. Second, the procedural framework, where we actually decode the questions. Third, top examiner mistakes, where we look at the traps. And finally, critical and comparative analysis.
Section 1. Core OOP principles. The theoretical architecture. This is our foundation. Before we can build the house, we need to understand exactly why the Cambridge Assessment Framework prioritizes analytical depth over superficial breadth. Our absolute first core definition in this architecture is the object. Now, listen closely. An object is an instance of a class requiring precise definition within the theoretical architecture. In a practical, high-stakes exam scenario, let's say a question asks you to model a computerized library system. The book itself is the class, but the specific physical copy of the Matrix DVD or the Matrix book that you actually borrow, that specific item is the object. It is an instantiated entity taking up actual measurable memory in the system. Now, let's look at how our student Alex handles this. A typical, flawed exam answer from Alex would just say, an object is a thing in the code that holds data. Guess what? 0 marks. The examiner is not looking for vague approximations. They are looking for precise surgical definitions. You need to explicitly state that an object is a specific instantiated realization of a class template that seamlessly encapsulates both data and behavior. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, so to get those marks, you need to use the PEAL framework. Point, evidence, explanation, link. We will use this to structure every single answer. Instead of a vague guess, your point is that the object is an instantiated entity. Your evidence is that it takes up specific memory for the Matrix DVD. Your explanation is that it bundles the data and behavior together. And your link connects it right back to the library system the question asked about. That is how you guarantee the marks. Next up in our terminology matrix, properties and attributes. These are the strictly defined data points or states associated with an object. Going back to our library example, the attributes of our specific book object would be things like its title, its author, its unique ISBN, and its current systemic state. Meaning, is it currently checked out or is it available on the shelf? Now, a common mistake, and this is exactly what Sam does when rushing through a paper, is to simply state attributes are basically just variables. Again, that's not going to cut it for top marks. It's too simplistic. Top-tier candidates explicitly connect these specific terms to other syllabus areas to demonstrate deep integrated knowledge. They don't just say variables. They mention how attributes utilize specific data types derived from procedural programming, like strings for the title or booleans for the availability state. Furthermore, they discuss how the concept of encapsulation actively protects these exact properties from unauthorized external modification. They show the examiner that they see the whole board, not just a single piece. Let's move to our next interconnected concept, Methods. These are the behaviors, actions, or specific algorithms that an object executes. Think about it in grammatical terms. If your attributes are the nouns and the adjectives describing your object, then your methods are unequivocally the verbs. They do the heavy lifting. In our ongoing library system scenario, methods would be functions like checkout, return book, or calculate late fee. Now notice the direct causal relationship here. This is absolutely critical. An object's methods are specifically intentionally designed to interact with and modify that specific object's properties. You literally cannot separate the two. A method relies entirely on the precisely defined state of the object to execute its underlying algorithms accurately. For example, the checkout method must first read the isAvailable attribute. If the attribute is false, the method must reject the action. Understanding and explaining this exact linkage in your answers is what pushes you up those grade boundaries from a B to an A star. It shows you understand the dynamic relationship within the code, not just static definitions. Finally, to cleanly complete our theoretical architecture, we have classes. A class is the blueprint or overarching template from which specific objects are instantiated. The class is the abstract, conceptual design. The object is the concrete, functional reality. Think of the class as the incredibly detailed architectural blueprints for a massive house. You can't live in a blueprint, right? But the object is the actual house built from those blueprints, the one you can actually walk into with real doors and windows. When you define a class in an exam paper, you are defining the exact, rigid properties and methods that every single object instantiated from that blueprint will absolutely possess. It's the DNA of your program. That beautifully concludes our theoretical foundation. But here is the reality check. Simply knowing the theory isn't the real challenge of the Cambridge exams, is it? Any student can memorize a textbook. The real test is application.
Now, what's really interesting about this slide is this pivotal question we have to ask ourselves. Why do smart, capable students find applying these core concepts to unfamiliar contexts so incredibly hard? You know all the definitions we just covered, but then you sit in the freezing cold exam hall, you open the paper, and suddenly they aren't asking about a library anymore. They are asking you to design an OOP system for a fully automated, synchronized drone delivery network. And boom, panic sets in. Sam's mind goes blank. Why? Because students are usually trained to memorize specific, rigid scenarios rather than applying a systematic, flexible framework. You are looking at the superficial paper, not the underlying code patterns. To fix this immediately, we have to transition from abstract theory to methodical, battle-tested exam application. We need to decode the command words.
Section 2. The procedural framework. Decoding the questions. This is where the magic happens. This is where we take those deeply flawed answers, apply systematic processing, and use algorithmic thinking to unlock top marks. Here is the absolute game changer that most teachers forget to tell you: the method mark strategy. Examiners actively award marks for the analytical process, not just the flawless final result. Let that sink in. The examiners actually want to give you marks. If you write out a massive, complex algorithm for an OOP method under intense time pressure, and you make a tiny, silly syntax error on the very last line, maybe you forget a semicolon or misspell a variable, you absolutely do not lose all the marks. The examiner's job is to trace your logical, structured reasoning. They are looking at your thought process. Did you identify the correct object from the scenario? Check, that's a mark. Did you attempt to access the correct attribute? Check, another mark. Did you initiate the proper loop structure? Check. Those are all method marks. Your structured, visible reasoning on the page is the skeleton key that actually unlocks the grade, even if the final execution isn't entirely flawless. But to capture those method marks, you can't just brain dump like Alex. You need a system. To systematically maximize those method marks every single time, top candidates use a standardized 5-step sequence. It's an algorithm for taking exams. Let's walk through it. Step 1. Deconstruct the question. What exactly is the command word asking you to do? If the examiner uses the word describe, they are looking for characteristics. If they say evaluate, they want pros, cons, and a highly justified conclusion. If you treat an evaluate question like a describe question, your mark potential drops to 50% immediately. Step 2. Extract relevant data. Take your pen and literally highlight the nouns and verbs in the exam scenario. The nouns become your classes and attributes. The verbs become your methods. Step 3. Select an analytical framework. Will you use a structured Peel paragraph for a written response, or will you use standard pseudocode conventions for a programming task? Decide before you write. Step 4. Execute with clear notation. Write cleanly so the examiner can actually read your logic. Step 5.
Present with perfectly correct terminology. Don't say thing, say object. Don't say variable, say attribute. If you strictly follow this 5-step algorithm, you will methodically dismantle even the most terrifying, complex past paper problems. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at aceexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Top examiner mistakes, the traps. We've meticulously analyzed the principal examiner reports from Cambridge, and there are specific, repeated places where students consistently bleed marks year after year. Let's test your pattern recognition with our interactive workshop right now. Here are the top 3 explicit examiner warnings. Trap 1. Using the wrong formula or algorithm for the context. Trap 2. Forgetting boundary conditions and edge cases. Trap 3. Providing answers that are not specifically tied to the given context. We are going to do a live 60-second challenge right now. I want you to imagine a complex data table on your screen mapping a bank account class. You are asked to write a method to withdraw funds. What is the absolutely critical boundary condition here? Think about it. Instantly, your brain should be screaming, check if the balance drops below 0. Trap 2 catches so many students because they write the math perfectly, but forget to test the edge case of an overdrawn account. Now for challenge 2, find the flaw. Listen very closely to this flawed sample paragraph that our student Alex wrote. The system uses objects to store data, and methods are used to change things. Did you catch the flaw? It completely falls into trap 3. It is entirely generic. The examiner's commentary on this exact type of answer is brutal. It says, candidate provided a textbook definition with 0 application. It is not specific to the context given in the question. To fix this and push that mark potential from 0% to 100%, you must explicitly name the specific objects, like the customer account, and the specific data being changed, like the account balance. So, the crucial overarching point is this massive examiner alert right from Cambridge. Candidates consistently confuse key terminology, always define terms before using them in extended responses. This is a direct, incredibly urgent warning from the principal examiner reports. When you are asked an essay-style question evaluating OOP against procedural programming, do not just start throwing around big buzzwords like encapsulation, inheritance, and polymorphism hoping they stick. You have to define them briefly in the explicit context of the question first. Let's do a 30-second speed writing visualization of a perfect Peel paragraph right now. Point: OOP is significantly more secure. Evidence: it utilizes the principle of encapsulation. Explanation: attributes are deliberately made private and can only be accessed or modified via controlled, public getter and setter methods. Link: therefore, in this specific banking context, unauthorized external functions absolutely cannot alter the account balance directly, preventing critical security breaches. Boom! That is a 100% mark paragraph. That is how you dominate the exam. Section 4. Critical and Comparative Analysis. Unlocking top marks. We are now officially stepping up to the higher order assessment objectives. This is no longer just about knowing what an object or a class is. This is about deep evaluation and sophisticated comparison. And this slide brilliantly illustrates the exact defining difference between an average candidate and an absolutely exceptional one. Superficial breadth versus analytical depth. An average candidate, like our rushing student Sam, will hastily list 5 very basic, high-level similarities between 2 programming paradigms and call it a day. That is superficial breadth. It's wide, but it's an inch deep. An exceptional candidate, however, provides deep, rigorously evidence-based comparative analysis. They intentionally use powerful comparative connectives like whereas, conversely, or in direct contrast. They actively support each comparison with hard evidence extracted straight from the scenario. And most importantly, they identify similarities and differences before drawing a highly justified conclusion about their relative importance. They don't just write a basic sentence like OOP is better because it's newer. No, they write, while object-oriented programming inherently requires significantly more initial design overhead and memory allocation, its robust modularity makes it significantly more maintainable for the automated drone delivery system's rapidly expanding complex codebase. Do you see the difference? It's night and day. To truly master this level of output, you need to deeply internalize the 4 pillars of evaluative thinking. Pillar 1, considering multiple solutions. Never pretend there is only one way to code a system. Discuss the alternatives. Pillar 2, analyzing trade-offs. This is massive. Everything, literally everything in computer science, is a fundamental trade-off between memory footprint, processing speed, and developer time. Mentioning this dynamic always scores highly. Pillar 3. Acknowledging limitations. No system architecture is perfectly flawless. Confidently state the realistic flaws or potential bottlenecks in your own proposed design. Pillar 4. Justifying decisions with evidence. Always back up your final recommendation with specific facts from the case study provided. This is the ultimate master-level blueprint. If you consciously combine these 4 pillars with structured reasoning and precise, textbook-accurate OOP terminology, you create an answering system that is practically bulletproof against any examiner's red pen.
So we've broken down the code. The entire computer science answering system boils down to 3 unbreakable rules that guarantee top marks. Rule 1, command word decoding. Rule 2, Peel framework application. And Rule 3, utilizing a strict time management matrix so you never rush like Sam. I leave you with a final, highly provocative question. Will you go back to just randomly memorizing textbook terms, or will you use this methodology to finally see the underlying, predictable patterns behind every single exam question? The choice is entirely yours. Command word decoding, structured framework application, and rigorous analytical depth. That is your blueprint for complete success. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @theexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the bookist challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep decoding the matrix.